Okay, so as another example, it's sometimes not possible to bring together any two ions in a way that would form a precipitate. And an example, not to spoil the surprise too much, is this reaction here, sodium chloride and potassium nitrate. Those are both soluble in water. And in this type of reaction, you would expect, if you were going to form any products, that it would just be obtained by rearranging, or basically taking the positive ion of one reactant and combining it with the negative ion of the other reactant. So you would expect sodium nitrate and potassium chloride as your products. Everything here is 1-to-1. Sodium is +1, chloride is -1, potassium is +1, nitrate ion is -1. So we don't have to worry about balancing it. It's already balanced. And the products, well, if you look up the products, all potassium compounds are soluble, and so KCl will be aqueous. Also, all sodium compounds are soluble, and all nitrate compounds are soluble too. So sodium nitrate is very definitely aqueous. That's dissolved in water. When both of the reactants and both of the products are all aqueous, that's a pretty good sign that you actually have no reaction. And what you really have are just a bunch of ions sitting around in water doing nothing. You can always prove that, though, by writing the ionic and net ionic equations, because that will actually end up proving whether there's a reaction or no reaction. So for the ionic equation, sodium chloride is aqueous, which means it's actually present as Na plus and Cl minus ions. And KNO3 is also aqueous. That means it's actually present as K plus and NO3 minus ions. And as for the products, KCl is aqueous, which means it's actually present as K plus ions and Cl minus ions. And NaNO3 is also aqueous, meaning it's actually present as Na plus ions and NO3 minus ions. So this would be your ionic equation, where you basically take things and represent them the way they really are in solution. That is, any ionic compound that's listed as aqueous will be soluble, and therefore will be present as separate independent ions instead of intact molecules. When we look at the net ionic equation, well, the first thing we have to do is go back to the ionic equation and cancel out the spectator ions. That is, any ion that comes out exactly the same as it went in. So if an ion goes in as an ion and it comes out as part of a compound, that's a change. So that ion has to stay. But if the ion comes out as an ion with the same charge and with the same number of ions, then that's a spectator ion and you can cancel it out. Well, the Na plus ion comes out as an Na plus ion. That's a spectator ion. The Cl minus ion comes out as one Cl minus ion. That's also a spectator ion. The K plus ion comes out as a K plus ion. That's a spectator ion. That can go. Can you see what's happening here? The NO3 minus ion comes out exactly the same as it went in, as one NO3 minus ion. So that goes. They're all spectator ions. And by the time you get to the net ionic equation, there's literally no reaction left because they're all spectator ions and they all cancel out. So this reaction, in fact, does not occur. What you've really got is just a bunch of ions sitting around in solution. Those products never actually form. Okay, so that's basically how it often works out when there's no reaction. Section 4.7 is where the book formally introduces the idea of molecular ionic and not ionic equations. I introduced them earlier because I thought it made sense to introduce them before the book does. But this is where we really get into the meat of things, and so I'll show several more examples of molecular ionic and not ionic equations. There's more than one way to remove ions from solution, as I've mentioned before, actually. One way is to form a precipitate. But another way would be to form a gas, which bubbles out into the air and gets lost from solution. Another way would be to form a product that's not ionic, like water. You know, water is certainly soluble in water, but it's not an ionic compound, so it's not ionized. So the ions that go into forming the water will, well, technically, I guess they're still in solution, but they're no longer ions. And so that would be a way of removing ions from solution. And, well, actually, another example would say if you can form a weak acid. Weak acids would be soluble in water, but they're not ionized. And so that would be kind of the same idea. Okay, so some examples of that would be acid-base reactions. Hydrochloric acid and, say, potassium hydroxide. Hydrochloric acid is obviously an acid. Potassium hydroxide is a base. And when you mix acids and bases, what you get is a type of reaction that's actually the type of reaction that we've been seeing as the examples so far are all known as double displacement reactions, which just means that the positive and negative ions of the two reactants switch partners. And so, as we saw before, that's what happened in the last example. The sodium ion came in with the chloride ion, it came out with a nitrate ion. Potassium ion went in with the nitrate ion, came out with the chloride ion as the possible products. Well, here the possible products would be KCl, potassium chloride. And if you look that up, being a potassium compound, it is definitely soluble in water, so you can list that as being aqueous. The other product would be hydrogen hydroxide. That is, the positive ion from HCl and the negative ion from KOH would be HOH, hydrogen hydroxide, but HOH is better known as water, or H2O. So that is basically the two products of acid-base reactions will be an ionic compound like KCl and water, because the acid will give off H+ ions and the base will give off OH- ions. And when H+ and OH- come together, they form H2O, or water. Water is not considered aqueous. It's considered to be a pure liquid. And so you would list that as H2O with a little L after it. That's the molecular equation. For the ionic equation, we'd look at each of the reactants and products in turn, and if they are ionized in solution, then that's how we write them. And if they're not ionized in solution, then we write them as intact molecules. For the HCl, we have, that is a strong acid, and so it will be present as H plus and Cl minus. Remember, acids are molecular type compounds, but they ionize when you put them in water. So H plus and Cl minus. Potassium hydroxide will be present as K plus and OH minus. Remember, the polyatomic ions like hydroxide will come apart from the rest of the molecule, but the polyatomic ions themselves remain intact. So it's OH minus. And in the products, we've already determined that KCl is a soluble ionic compound. So that will be present as K plus and Cl minus. But water is not an ionic compound. And unlike acids, it does not ionize in water either. So H2O has to be written as H2O because that's how it's really present. And because of that, because you formed that compound that's not ionized, this reaction actually does occur. There's your driving force right there, the H2O. And we can write a net ionic equation for it after eliminating the spectator ions. Now, when we come to the H plus, remember H plus comes out as part of H2O. That's a change, so that is not a spectator ion. We have to keep the H plus. The Cl minus, though, comes out as Cl minus. That means Cl minus is a spectator ion. The K plus comes out as K plus. That means K plus is a spectator ion, and that can go. Okay, so eliminating the spectator ions is what we're doing now. The OH minus comes out as part of H2O. That makes that a change, and that is not a spectator ion. So OH minus has to stay, as does the H2O. So your net ionic equation is H plus plus OH minus produces H2O. Now that is basically the reaction boiled down just to what's changing. So that's what we're most concerned with. It's also the most universal expression of what's going on here. And what it means is anytime you get H plus ions together in solution with OH minus ions, they will come together to form H2O. And it doesn't matter where the H plus ions come from or where the OH minus ions come from. In other words, anytime you have an acid, which gives off H plus ions, and a base, which gives off OH minus ions together in solution at the same time, they will produce water as one of the products. And basically that's what that means. Okay, so that's another example of molecular ionic and net ionic equations. Another useful example would be what happens when you mix a strong acid, like hydroiodic acid, with a weak base, like barium hydroxide. You will get, again, a sort of mixing and matching of the positive and negative ions. You will get barium iodide as one of the products. And barium iodide, if you look it up, is insoluble in water. So we list that as solid. The other product is hydrogen hydroxide, better known as H2O. And that is a liquid. It's not considered aqueous even when it's dissolved in water. So that's the molecular equation. For the ionic equation, you take, again, each of the products and reactants and write them as they actually are in solution. That is, if they're ionic and soluble, you write them as separate ions, and otherwise you write them as intact molecules. HI is, well, again, it's not ionic, but it is an acid, which means that it is ionized in solution. So that'll be present as 2H plus 2I minus. Barium hydroxide is an ionic compound, and it is soluble in water. So that will be present as barium ions and, 2 times as many hydroxide ions. And now for the products, this is where it gets interesting. Barium iodide, we've already established, is insoluble in water. So it's not present as separate ions. So you don't write it that way. You write it as intact molecules. The water is not ionized in water either. So you write that as intact molecules. So for the net ionic equation, you go through the ionic equation, eliminate the spectator ions. So let's see, the H plus ions come out as part of H2O. That means they're not spectator ions, so they have to stay. The I minus ions come out as part of BaI2, so they're not spectator ions, so they have to stay. The Ba plus 2 ions come out as part of BaI2, so they're not spectator ions, so they have to stay. And the hydroxide ions come out as part of H2O, so they're not spectator ions, so they have to stay. Actually, there are no spectator ions. And your net ionic equation actually ends up being the same as the ionic equation. So if there are no spectator ions, that just means that the net ionic equation will be the same as the complete ionic equation, which saves you a little work, I guess, although it means that the net ionic equation is longer, so you have to write more. Okay, so if you have a molecular equation that's 2AgNO3, that is 2 silver nitrates, plus magnesium chloride, and those are both soluble ionic compounds. The products will be 2 silver chlorides. And if you look it up, silver chloride is insoluble in water. So there's your driving force for the reaction right there. You will also get magnesium nitrate. Being a nitrate type compound, this is soluble in water, so that's aqueous. For the ionic equation, you would both of the reactants are soluble ionic compounds, so you would write them as separate ions. So silver nitrate would be 2Ag plus 2NO3 minus. Don't forget that that 2 applies to the nitrate ion as well as the silver. Plus Mg plus 2 2Cl minus. And that will yield 2AgCl solid. So there's your driving force. And Mg plus 2 NO3 minuses. Now to do the net ionic equation, you just have to go through and eliminate the spectator ions. Silver ions come out as part of silver chloride, so they're not spectator ions, they have to stay. Nitrate ions, 2 of them, come out as 2 nitrate ions, so they are spectator ions and they can go. The magnesium ion also comes out exactly the same as it went in, So that's a spectator ion. And the chloride ions come out as part of AgCl. So they are not spectator ions and they have to stay. So your net ionic equation would be 2Ag plus 2Cl minus yields 2AgCl solids. But there's a catch. You may notice that all of these coefficients are divisible by 2. And as I've mentioned before, we generally want to have the lowest whole number ratios, whether it's a molecular formula, or sorry, an ionic formula, or an empirical formula, or the coefficients in a balanced chemical reaction. We want to have the lowest whole number ratios possible. Since all of these coefficients are divisible by 2, you would do that, and so your actual net ionic equation is Ag plus Cl minus yield AgCl solid. So that is the actual net ionic equation. And what that means, again, is it's more universal than the original equation. It tells you that anytime you get silver ions and chloride ions together in solution, they will come together to form silver chloride. And it doesn't matter where the silver and chloride ions come from or how they get into solution. It just matters that they're there. The next section is about acid, base, and gas evolution reactions. We've seen one or two examples of acid-base reactions. The gas evolution, well, we've seen, I think, maybe one or two gas evolution reactions also. Anyway, we go into acid-base reactions in much more detail in Chem 121. And so we're going to save this for basically the second summer session. So we're going to skip this for now and go on to section 4.9. 4.9 is oxidation reduction reactions. Oxidation reduction reactions are a very important part of chemistry. They represent some reactions that are very important, not only in chemistry, but to society in general. Much of our energy production in society is done by way of oxidation reduction reactions. Burning of anything is an oxidation reduction reaction. Also, the way that we get a lot of pure substances, particularly metals, will involve oxidation reduction reactions. Oxidation and reduction reactions are also known, as redox reactions, because redox is easier to say than oxidation reduction reactions. And also it's safe to combine the two words together like that because oxidation and reduction always occur together. Sometimes there are processes that we will refer to as oxidations and other procedure or other processes that we may refer to as reductions. And that's just because in those cases, the substance we're most interested in is being oxidized or reduced, as the case may be. But the other process is always going on at the same time. It's just that in some cases, the other process may involve something that we don't really care about. But they always go together. You can never have an oxidation without a reduction, and you can never have a reduction without an oxidation. Okay, these reactions involve the transfer of one or more electrons from one element to another. And so oxidation is one of those processes, reduction is the other. But basically, if something gives up an electron, that electron has to go somewhere. And if something gains an electron, that electron has to have come from somewhere. And many oxidation or reduction reactions also involve a reaction with oxidation or with oxygen or hydrogen. Oxygen being where the word oxidation comes from, in fact. So there are actually three different ways to define oxidation and reduction. In each case, oxidation and reduction are essentially the opposite of each other. So as I said, oxidation and reduction can involve reaction with an oxygen. And so an oxidation could be considered a gain of oxygen. If oxygen ends up making up a bigger proportion of the product than it did of the reactant, then that is often considered an oxidation. And the opposite would be reduction. If oxygen ends up making up less of the product than it did of the reactant, then that would be a reduction. Hydrogen is the opposite. If you lose hydrogen, relatively speaking, then that would be an oxidation. If you gain hydrogen, relatively speaking, that would be a reduction. The most important definition is the most modern definition, and it's the one that is sort of broadest, the most universal. That involves electrons. Loss of electrons is oxidation. And gain of electrons is reduction. And in fact, there's a handy way to remember it. Oops, let me get it all on screen there. There's a handy way to remember it based on the electron definition, and that is Leo says grrr. That is Leo the lion says grrr. Loss of electrons is oxidation. Gain of electrons is reduction. And so if you remember that, that'll make it easy to remember which is which. Because of these definitions, they're basically the opposite of each other, and they involve the transfer of something from one place to another. Once again, it bears repeating that these two processes always occur together. If something loses an electron in order to be oxidized, that electron has to go somewhere. The electron just can't sit around and exist on its own. It has to go into some other atom, and whatever atom is gaining the electron is being reduced. Or if an atom gains an electron in order to be reduced, that electron has to have come from somewhere, and wherever it came from, that was oxidized. So they always occur together. Some examples of oxidation reduction reactions would be, for example, the rusting of iron, or corrosion or tarnishing of any kind would be oxidation reduction. That's where 4 iron atoms combine with 3 molecules of oxygen to form 2 Fe2O3 molecules. Fe2O3 is iron 3 oxide, better known as rust. We often think of rusting as an oxidation because, you know, when rusting occurs to our car, it's the iron that makes up the steel in the car that gets oxidized to rust, and that's what we end up having to go to the body shop and pay hundreds of dollars to fix. And so that's what we really care about. At the same time, though, oxygen from the air is being reduced into the compound iron oxide. But, you know, the oxygen from the air is free, and there's plenty more where that came from, and we don't have to pay to fix it. And so we don't really care as much about that. And so that's why we think of rusting as an oxidation, even though there's also a reduction going on at the same time. Combustion, you know, as I mentioned, burning anything is always an oxidation reduction reaction. So for instance, propane combines with oxygen from the air, and you get carbon dioxide and water as the products. Okay. So that's combustion. And now the propane is the stuff we have to pay for, and that's being oxidized into carbon dioxide and water. And so we often think of this as an oxidation, even though oxygen from the air is at the same time being reduced. But again, the oxygen from the air is free, and there's plenty of it. We don't have to pay for it, so we don't really care as much about that. So we think of it as an oxidation because it's the stuff we have to pay for that's being oxidized. Combustion of hydrogen is also a form of oxidation reduction. And in fact, any reaction that involves a free element as either a product or a reactant is an oxidation reduction reaction. So for instance, if you react the element sodium with the element chlorine to form sodium chloride, that is an oxidation reduction reaction. Okay, so that'll do it for this segment of the lecture. I'll pick up there in the next segment in just a moment.